Hello everyone, my name is Ben Drinkstveit, and today I'll be presenting my oral compendium on Manuel Blum. Who is Manuel Blum? Blum was born April 26, 1938 in Caracas, Venezuela. He attended MIT where he received a bachelor's and master's degree in electrical engineering and a PhD in mathematics in 1964. From 1968 to 2001, Blum worked at the University of California, Berkeley as a computer science professor, where he primarily focused on theoretical computer science. From 2001 to 2018, he worked as the Bruce Nelson Professor of Computer Science at Carnegie Mellon University, a prestigious position named after Bruce J. Nelson, inventor of the remote procedure call concept for computer network communications. In 1995, Blum received the ACM-AM Turing Award for his contributions to the foundations of computational complexity theory and its applications to cryptography and program checking. Today we'll be looking over several of his accomplishments that gained him such a reward. First off, we'll be looking at complexity. When Blum was doing research at MIT for his PhD, he became obsessed with complexity. It led him to develop two axioms in complex theory called Blum's axioms. The first being phi of the function m in input x is finite if and only if m of x halts. And the second being there is a computable procedure that given function x, input x, and outcome r, we can decide if phi of mx equals r. Basically, the amount of resources expanded by the program running a particular input can be computed unless the computation fails to halt, in which case it is undefined. This was well received by scholars in the field of computer science. It led to several developing theories, one such being Blum's own speed-up theorem. It suggests that if you have an algorithm for a particular function, you can modify it to run exponentially faster for the majority of inputs. However, the intriguing aspect is that this process can be repeated indefinitely. An infinite sequence of exponential improvement can be made to the algorithm. The concept is rather abstract and overall not very useful. However, this theorem serves as a cautionary tale for complexity theorists. It highlights that unless resource bounds, such as time and space complexity, are constrained to well-behaved and familiar classes like polynomial and exponential, peculiar and counterintuitive outcomes can arise in the realm of computational complexity. Moving on, Blum wanted to do more than just analyze complexity. He wanted to see how it could be used to benefit other aspects of computer science. The first one he ended up looking in the early 1970s was cryptography. He came up with the coin toss over a phone problem. Basically, two individuals named Bob and Alice are trying to settle an argument over a phone. That argument is who should next buy drinks at the bar. They decide it will be decided by a coin flip, but what is stopping the coin flipper from lying? Blum demonstrated a solution that instead of directly revealing her choice to Bob, Alice calls the flip by announcing some data that commits her to her choice. This commitment involves creating a piece of information based on a secret bit, her choice, that later, with Alice's cooperation, can be used to reveal the bit. Importantly, this revelation process designed in such a way that it cannot be manipulated by Alice, and Bob cannot question its validity. The concept introduced here, known as commitment, involves creating a place of data that ties an individual to a specific choice without immediately disclosing that choice. Later, with proper collaboration, the committed data can be used to reveal the choice in a way that is secure and tamper-resistant. This notion of commitment has proven to be a valuable tool in cryptography with applications in ensuring the integrity and fairness of information exchange, especially in situations where trust between two parties is limited. The concepts involve creating tamper-resistant data to bind individuals' choices, relying on computationally hard problems for security. Next, Blum dipped his toe into true random number generation. A common use of pseudo-number generation is to introduce randomness. However, Blum questioned the extent to which these generated numbers can be truly considered random. Blum proposed that the complexity of distinguishing the output of a good pseudo-number generator from truly random sequences is key factors. This challenge was considered difficult to solve, and many popular generators at the time failed this test. Ultimately, this resulted in Blum producing his own pseudo-number generator, the Blum-Blum-Shum, which followed the form of x n to the first equals x squared of nth mod m, where x0 is a random seed and the value of m is equal to p times q, where p and q are prime numbers. Blum demonstrated that this generator has cryptographic strength. He, along with his student Shafi Goldwasser, in 1986 devised public key encryption scheme based on the Blum Shub generator. Unlike RSA, this scheme has a mathematical proof supporting its resilience against attacks, specifically showing its difficulty to break is equivalent to challenging of factoring. Next, Blum wanted to try his hand at program checking. In mid-1980s, Blum proposed the question, is it possible to build a program to check if other programs work as intended? This resulted in him and his students developing several checkers. However, none were ever considered that profane and ultimately considered not very useful. Though not directly aiding practical software testing, this work inspired the concept of interactive proof. It led to the 1991 PCP, probabilistically checkable proof theorem, showing any proof's correctness can be reliably tested by examining just a few bits, accumulating in a breakthrough for a complexity theorist. Verifying a solver, oopsies, sorry. And last, Blum's latest achievement is the CAPTCHA system. In our growing network environment, Blum became concerned of the emergence of malicious bots. Blum looked for a solution to verify real users over bots by using the inherent difficulty of solving complex problems. This led to the creation of CAPTCHA, a completely automated public Turing test to tell computers and humans apart. CAPTCHA exploits the fact that certain tasks like recognizing distorted characters in an image or solving puzzles are relatively easy for humans to do with their cognitive abilities and pattern recognition skills, where for the computer, that is highly complex task. Modern AI has made the CAPTCHA less effective, however, it is still being used to protect web pages and develop stronger methods of detecting non-human users. I bet anyone watching this can relate to the frustration of the traffic light situation. It's hard for computers, but it's hard for humans too. Thank you for your time. Here are my references.